Well, dear students, in this video I am going to discuss P-type semiconductors. P-type, pure semiconductor silicon germanium. So their conductivity because of electrons hole created due to thermal excitation. In last video I explained you N-type semiconductor that conduct electricity even at 0 Kelvin because of donor electron. Similarly, which is P-type semiconductor? The semiconductors obtained by doping pure semiconductor like silicon or germanium with trivalent elements, aluminum or indium, are called P-type semiconductors. Actually, people may define other way also. When 14 group element, अरे भाई simply कहिए ना pure semiconductor. The extrinsic semiconductors are obtained by doping the pure semiconductor with trivalent और pentavalent. Simple बात है ना. तो जैसे कि बहुत बातें हैं इस तरह की जो अलग अलग लोग अलग अलग तरह बात करते हैं, but we must be very plain. तो semiconductors obtained by doping pure semiconductors like silicon germanium with trivalent element, these are 13 group elements, are called P-type semiconductor. Then how their conductivity is different from pure semiconductor? I will take again here the covalent bonding as well as energy band diagram, just to explain the conductivity. Suppose it is aluminum atom here, aluminum atom. These are silicon atoms. These are silicon atoms. So silicon atoms, have 4 valence electron. Aluminum has 3 valence electron. Silicon, 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 silicon. So aluminum, trivalent atom. It has only 3 valence electron. Then how it will make covalent bonding? It will take electron from neighboring bond between silicon atoms and it will accept electron. And therefore here aluminum is called acceptor atom. Acceptor atom. It accepts electron from neighboring covalent bonding between silicon atoms, creating a hole there, even at 0 Kelvin. Even at 0 Kelvin, there will be a hole in the covalent bonding between silicon atoms. Silicon atoms के बीच में. Aluminum takes this electron from here, create hole here. Acceptor atom by trivalent aluminum 13 here 27 like that. As soon as it will get electron from the neighboring, it becomes negatively charged, partial negative charge. So this this hole created here is bound with acceptor atom. So its energy will be different from the energy of electrons present in valence band due to thermalization of pure semiconductor. Have you got my point? But this hole also does not remain stationary. It is at any temperature will be filled up by taking electron from here and then here and so on. So it will keep on revolving around the acceptor atom. Around the acceptor atom. Here aluminum is called acceptor atom. The number of holes here will be equal to number of dopant aluminum atom. So even at 0 Kelvin it will show conductivity. Because of added impurity, there is a hole already there. There is no need of thermalization. And here I told you that number of hole is equal to number of acceptor atom, and here hence number of hole per unit volume will be much greater than any. Any means number of electron. At ordinary temperature, room temperature, some electrons holes are present because of thermalization, but that number of hole per unit volume, this number of hole per unit volume is much greater than any. Hole act as positive charge carrier, therefore these are called p-type semiconductor. The letter P has been derived from positive because hole act positive charge carrier, and therefore this semiconductor obtained by doping with the trivalent element is called p-type semiconductor. Now, how we can explain the conductivity on the basis of band diagram? It is valence band here. You are familiar with this. This is energy gap less than 3 electron volt. Please remember this 3 electron volt. अभी आपको बहुत कुछ याद रखने की जरूरत है. If you want to be expert of the subject, some things should be learned. This is valence band here. Oh, sorry. This is conduction band. This is valence band. At room temperature, some hole will be already present. Some hole electron are there. Now, energy of this hole will either lie in valence band or in conduction band. Here valence band completely occupied by electrons, except a few energy level, which are created because of thermalization. Electron gain energy and go into conduction band. But where is the energy of this hole? The energy of this hole will be just above the uppermost energy level. The energy of hole will be just little above the uppermost energy level of conduction band, and this is called acceptor energy level. You are asked in exam to draw the energy level diagram of p-type and n-type semiconductor also. Or you may be given this diagram and you may be asked, this diagram is for which type of semiconductor. So this dotted line represents the energy level of acceptor hole. Aluminum become negatively charged. So this is called energy level of hole acceptor, hole carried due to acceptor atom, and it called energy level. When we apply electric field, electron take this hole take energy go into valence band. In fact, holes show conductivity when they are in valence band. Electrons they show conductivity when they are present in conduction band. In last video I told you why the conductivity of semiconductors increases with the increase of temperature. So I told you that when we increase temperature, number of electrons in conduction band and hole in valence band increases, and this increased number of electron hole is called increase the conductivity. So I hope you have got my p-type semiconductor. Now how the doping is done? There may be a question in your brain, okay, how doping is done. In chemistry you have learned metallurgy. You have learned about alloys, how the alloys are produced. Alloys are the mixture of metal and non-metal or metals also. To produce an alloy, we melt the metal. हम metal को melt करते हैं. And in that melted material, we mix the desired quantity of impurity. Then after mixing that, we cool the material, we get solid, and that solid is an alloy. Now you may be thinking, why these are in majority, how much is this? So here there is a question in NCERT book. Please see this. Here you are given a question. Suppose that pure silicon crystal has 5 to 10 to the power 28 atoms per meter cube. Pure silicon has 10 to the power 28 atoms per meter cube. It is doped with pentavalent arsenic at rate of 1 ppm. 1 ppm, this is the term here used, means 1 part per million. 1 part per million. Million बड़ा million ही है. 1 part per million. Calculate the number of electrons and holes. Given Ni integer density is equal to 1.5 10 to the power 16 per meter cube. Silicon is doped with at rate of 1 ppm by arsenic. Arsenic is pentavalent, so number of electrons will be equal to number of donor atom. Number of electrons equal to number of donor atoms. It is equal to actually 10 to the power 6 among 10 to the power 6 silicon atom there is one arsenic atom. So the number of silicon atom, number of donor atom is equal to 10 to the power 28 upon 10 to the power 6. By among 10 to the power 6 silicon atom there is one, and with one there is one upon this and with this. I hope you have got my point. 10 to the power 22. So 10 to the power 22 are the electrons per meter cube. N. So N equal to 22 per meter cube. Now how to calculate holes? Just now I told you that Ne into Nh is equal to Ni square. This is true everywhere. Ne 10 to the power 22 into Nh is equal to 1.5 into 10 to the power 16 square. We are given Ni, intrinsic charge carrier density. This example is very important for understanding point of view. कि कितने जोड़ते होंगे हम, कैसे निकलता होगा हम ये सोचते रह गए थे. When I was student, actually we learned the semiconductor in our postgraduate classes. You are learning here in class 12, so you are lucky enough. Please study properly, get knowledge and apply that to your daily routine work, and what is happening around us, apply to that. Don't go into blind faith कि वो भगवान की माया है ना. बहुत बच्चे ऐसे सोचते रहते हैं, पढ़े लिखे भी सोचते रहते हैं ऐसे ही. तो NH square of this 2.25 into 10 to the power 32 upon 10 to the power 22. So it is 2.25 10 to the power कितना हो गया भाई? कुछ गलत हो गया डाटा. क्या गलत हुआ हमसे? नंबर सही नहीं है ना. Oh yes, वो 5 into 10 to the power, sorry भाई, सारा गलत हो गया. वो 5 into 10 to the power 28 था भाई, number of silicon atom. So it will be here 5 into this. तो 5 यहाँ भी आएगा. Sorry, number of silicon atom per meter cube 5 into 10 to the power 28 per meter cube. So Ne will be this. Because 10 to the power divided by 10 to the power 6, so this will be. Okay. So it is 10 to the power 10. So 0.45 10 to the power 10. Or 4.5 into 10 to the power 9. Nh per meter cube. And whole were there 5 into 10 to the power 22. 10 to the power 22 are the number of electrons, and 4.5 10 to the power 9 per meter cube are the whole. So this number is extremely high, and so we can neglect. When we are calculating conductivity, I will tell you, in case of conductor, electron hole both are charge carrier, and the current will be there due to current of holes and electron. So current due to hole will be of this order while it is 10 to the power 22. So here negative charge carrier are the majority, and hence it will be a N-type semiconductor. I hope you have got my point. So I have explained N-type, P-type pure semiconductor and some intrinsic charge carrier density, etc. In coming videos I will be taking here semiconductor devices. The chapter is very important, but I don't know why the syllabus has been deleted now. In the name of coronavirus, syllabus has been deleted and deleted and deleted. from where student will get the knowledge. It is matter of sorrow for me, may not be for you. If you like my video, please like and share the video. I ask your friend to please subscribe the video. It will encourage me to do work for the students. If we don't get any encouragement from student side, then we feel a little nervous and feel that nobody is accepting our work, but you have to learn. Thank you. मिलते हैं